This is section 7.4 and it's on vectors and applications. And we will work with vectors in this section and the next one. Some basic terminology. Quantities that involve magnitudes, such as 45 pounds or 60 miles per hour, can be represented by real numbers called scalars. Other quantities, called vector quantities, or just vectors, involve both magnitude and direction. A vector quantity can be represented with a directed line segment, a segment that uses an arrowhead to indicate direction, called a vector. The length of the vector represents the magnitude of the vector quantity. I'm going to draw you a picture of a vector. And we've just been working with scalars so far in this class. A vector involves two parts: a direction and a length. So this is a vector. It should be a straight line with an arrow at just one end. And I'll call this vector V. To denote that it's a vector, I put a little arrow over it. And when you're reading the notes and the book and MyMathLab, you'll see that instead of having an arrow over the letter, it'll show it bold. Whenever it's bold, that represents a vector. And they just do that instead of putting the arrow above it. To describe the magnitude of the vector, we use absolute value signs. And we'll get more into this later on in the next section. But that's the magnitude of the vector. When two letters name a vector, the first indicates the initial point, and the second indicates the terminal point of the vector. If we come back to this vector over here, I'm going to label the initial point P and the terminal point Q. We could label this vector as V, or you could label it as PQ. Two vectors are equal if and only if they have the same direction and the same magnitude. If we have vector U, and then the vector V has the same magnitude and direction as U, then we can say that U is equal to vector V. The sum of two vectors is also a vector. Vector addition is commutative. The vector sum A plus B is the resultant of vectors A and B. If we have vector A, it looks like this, and then vector B, the sum is commutative. So we could add A, and then I could take B and bring it up here. And then I could put another A over here. This should be a parallelogram. If we add A, vector A and vector B, what you do is you just put the initial point of B and the terminal point of A. Then we have this final vector going from the initial point of A to the terminal point of B. And this vector is the sum vector. And this vector also represents the sum of B plus A. So if we take B and then plus A, we have the same terminal point, same initial point as the resultant vector A plus B. The next part, for every vector V, there is a vector negative V that has the same magnitude as V, but opposite direction. If I draw a vector V, and it has the same, another vector has the same magnitude, but it's in the opposite direction, then this would be negative V. Vector negative V is the opposite of V. The sum of V and negative V has magnitude 0, and is the 0 vector. So the 0 vector has no magnitude and no direction. Geometric properties of parallelograms. When you're adding vectors together, you can use a parallelogram to draw that. A parallelogram is a quadrilateral whose opposite sides are parallel. You can see that here. We have a parallelogram. Opposite sides are parallel to each other. Number 2, the opposite sides and opposite angles of a parallelogram are equal. This angle is the same as this measure. This angle measure has the same measure as that one. And the adjacent angles of a parallelogram are supplementary. That means that this angle is supplementary to this angle here. If you add those two angles together, they should add up to 180 degrees. Number 3, the diagonals of a parallelogram bisect each other, but they do not necessarily bisect the angles of the parallelogram. This diagonal does not bisect these angles necessarily, but if you draw another diagonal in this direction, they bisect each other. So that means that this length and this length are the same, and this length is the same as this length here. Going on to page 7-18, right in the middle it says the equilibrant of vector u is the vector negative u. And you'll use that in the next example, example 2.